Hi everyone, welcome to this lecture. So this lecture is a part 3 of project 1. So in project 1, we have manually applied least square method and we have calculated the value of bias and we have calculated the value of weight. Now it's time to test the model and evaluate the model. Now we do not have a testing data in our project 1 because we have used all the data during the training. So if you remember, if I go back, we had 30 samples in our data set. So these are the samples in our data set, and we have used all these 30 samples for the training. Now it's time to test the model. For test model, we will generate our own test data. So how we will generate our test data? We will take the help from the training data to generate our test data. So we have 30 samples in our training. So we will generate 30 samples for our test data as well. So if I go back and if I want to see the minimum value of my feature, so the minimum value of my feature is 1.1 and the maximum value of my feature is 10.5. So what I can do is that I can generate my test data. I can generate the 30 sample of my test data and I will take the minimum value of 0 and the maximum value of 11 so that the test data should be correlated with the trained data. So with the help of trained data, I am using the minimum value of the trained data, the maximum value of the trained data, and I am using same number of samples which were present in the trained data, that is 30 sample. So here I am generating a test data for 30 sample. So here I have generated and we can see the test data. Its minimum value is 0, its maximum value is 11, and we have 30 samples. Now similarly, we can generate test labels as well. So I am using the 30 values for test label because we know that if we have 30 test samples, we need 30 test labels. Now I am generating the test label using np.linspace. So my first input to this function is the minimum value of y. So these are my true values or these are my targets in the original data set. And I am taking the maximum value of y. So if I go back, I have the value of y. So that is my y. So there will be a minimum value here and there will be a maximum value here. So I am taking the minimum and maximum value of y in order to generate my test label. So I have generated my test label. So these are my test label. So in this way, student, you have learned that if you do not have a test data for a regression, or if your training data is very small and you have used all the samples of your training data for a training purpose and there is no sample left for testing the model, so you can generate your own testing data for regression problem. So here we have generated the testing data, we have generated the test labels as well. Now it's time to get the prediction from our model. So we have already calculated the value of W0, which is bias. We have calculated the value of W1. Now we are using this equation, which is the standard regression equation for simple linear regression, that to get the prediction, we need W0 plus W1x. So W0 plus W1x, here x is our test data. So if I run this cell, I will be able to generate the predictions. So in this way, we have used our test data. We use the weight and bias, which we have already calculated manually with the help of least square method to find out the prediction from the model. So these are the predicted value from the test from the model, and these are the original test data. Now it's time to visualize the model performance. So basically, if I go back, this is the scatter plot of my training data. So this is the scatter plot of my training data. Now my model has been trained and I have calculated the predictions from the model. It's time to draw the straight line on this training data and see how our model is performing. So we have calculated the value of y pred, that is, we have calculated the predictions from our test data. Now it's time to visualize the performance. So in order to visualize the performance, I will plot a straight line using my test data and using my y predictions, and I will put a color of blue. This is my scatter plot of my training data set. So in this way, I will check how my line is performing. So if we see a further code, this is my X label, which is independent data, dependent data. So this is almost the same code which we use to visualize our training data. So we can see that we have drawn the straight line and we are getting the predicted value. So these were our target values, which were shown in green dots, and this is our predicted value. So this is our linear regression model. And this model is trying very hard to fit all the points. But definitely there are errors because every point is not on the line. Few of the points are very close to line and few of the points are at some distance from the line. So in this case, all the target values and the predicted values are not same. Therefore, we have to calculate the error in order to evaluate the model performance. So we know that we have three kind of evaluation matrices, that is root mean square error, mean absolute error, and R square value. So first we are going to calculate root mean square error. So this is the equation of root mean square error. So the first step is that I am initializing root mean square error equals to 0. Then I will apply a for loop for all my 30 sample. I have 30 sample in a training data and I have a 30 sample in a test data as well. So this for loop will run for 30 times, that is, which is equals to the length of test labels. Now here I am calculating the predictions for all the 30 samples. Here I am adding. So basically, if you see this is test label minus y predict. So this is my error, y minus y pred. Then I am squaring it according to the equation, and here I am adding it. So here I am getting the root, I am getting the square value. Here I am dividing it with the total length. That is, I am calculating the mean, and finally I am taking the square root. So this is my final square root value. If I run this, I will get the root mean square 6197. So again, I want to go through this code. So first step was to initialize root mean square error, which is equals to 0. Here I am calculating the predictions for all the 30 samples by using a for loop. Here I am calculating the error. So error is the difference between this is y, these are the original test label and these are the predicted. So this is this bracket, this is the difference between the y and y pred. Then I am squaring it. Then here I am dividing with the total test labels, that is n. And then I am taking the square root using command np.square root. So here is my root mean square value. So now whether this value is good or not, we have to compare it with the value of test labels. So if I generate test labels here in order to compare the value test labels, in order to compare the values, so I can see that my root mean square is 6197, whereas my y values on my test labels values are in 40,000, in 43,000, in 55,000, and the minimum value is 37,000. So as compared to 37,000, this 6,000 is a very small value. So in this case, we can consider that our model is performing well. Now it's time to calculate another matrix, which is mean absolute error. So the steps are same. First, we will initialize mean absolute error. Then I am applying a for loop for 30 times, that is the length of a test labels, because the length of test label is 30. Here I am calculating the predicted value. Here I am calculating the absolute. So if you remember, in root mean square, we calculated the square value. Here you can see we have using the word absolute, ABS, and here is the difference y minus y pred. So here I am dividing with the n, that is to calculate the mean, and here I am calculating the mean. So all the steps are same. So this is 5247. This is even less than this value. It means our model is performing well. So both of these metrics suggesting that our performance is very well. Now it's time to calculate R square, and we know this is the equation of R square, 1 minus sum of square error divided by SST sum of total square. Now how to calculate? So all these steps are same. We need to calculate SSE and SST. So we put SSE and SST equals to 0. Basically, we have initialized this value. Now we are applying the for loop, which is equal to the length of test label. So we have 30 test labels. So this loop will run for 30 times. That is, it will run for every test sample. Here we are calculating y pred value. And you see here we are calculating SSE for every sample, and we are adding the values. That is, we are going to calculate this sign of summation. So we are adding every new value to the previous value. So this is the difference. This is y. minus y pred. Here it is square for SSE. This is y minus y mean. Here we are calculating the mean. If you see r square, we need to calculate the mean, and here we are squaring it. After getting the value SSE over SST, we are subtracting this ratio to 1. If I run this, I can see that this is a very good value. We are very close to 1. And we know that r square equals to 1 is an ideal value, or it is the maximum value. So in this way, by using all three metrics, we can see that our model is performing very, very well. So we have completed the manual implementation of least square. Let me go through it again quickly. So the first step was that we read our data set, which was regression underscore data. After that, we find the value of x and y from the data set. After that, we apply least square method manually. For this, we constructed three matrices y, x, and w. After that, we appending 1 at the first column of x, which is necessary in order to multiply x and w. So we generated ones, and here we appended the value of 1 to the x. And here we are applying 5 steps of a least square method. We calculate the value of bias, we calculate the value of weights, then we test our model. We generated our own test data. We also generated the labels for our test data. We get the predictions, we visualize the performance, and we can see that our straight line is fitting on our data very well. We calculate the error, then we calculate root mean square error, we calculate mean absolute error, and we calculate the value of r square. So we can see that all these matrices are suggesting that our model is performing well. Now we have implemented least square method manually, which is taking too long. So the other easy method is to use scikit-learn. Now I am repeating the same problem, but I am using scikit-learn. Scikit-learn is a scikit-learn library which is used to perform machine learning tasks. So every solution or every problem is solved with the help of this library. So the linear regression model is present in this library. Our metrics to evaluate the performance of linear regression are also present in this library. So we will use scikit-learn almost in our every code in order to solve the machine learning problem. So what I am going to do is I am importing linear regression from scikit-learn.linear model. And then here I am instantiating my linear regression, and I am saving it into LR variable. Let's run this cell. So I have imported. Now it's time to train. When we have a linear regression model, we will just use lr.fit xy. If you remember, x and y are our training data and our training labels. So the fit is used to train. The word fit is used to train the model. So scikit-learn is also using least square. So here we do not need to append one. We do not need to perform the 5 step which we performed for a manual implementation of a least square method. You just write lr.fit and it will take care of everything, and it will directly give you the value of your bias and your weight, which is a coefficient or intercept here. If you run this, we can see that this is the value of our bias, and this is the value of our weight. We can compare it to our manual value. It is 9449.96. So if I go back and see my weight, which I calculated manually, so the value of weight was 9449.96. So this is exactly the same value which is generated by scikit-learn, but it is taking very, very small step. That is only one step to calculate all the least square method. Now I have a test data. So here I am reshaping the test data in the form of column. Here I am getting prediction from the test data. If you remember, previously I used the equation of a linear regression, that is y is equals to w0 plus w1x in order to get the prediction. Here I did not use equation because scikit-learn is taking care of everything. I am just using lr.predict, and scikit-learn will give me the predictions here. So here I am getting the predictions. So this is the same line of code. You can see this is exactly the same model which we derived by using least square method manually. And now it's time to calculate the metrics. So RMSE, mean absolute error, and R square. So we can import this from scikit-learn, and the equation is, if you remember previously here, I calculated R square manually, I calculated mean absolute error manually, and I calculated root mean square manually. So we do not need to calculate these manually because all these matrices are present in scikit-learn. We just need to remember the equation. So for root mean square, we have to use matrix dot mean squared error. If you see matrix dot mean square error, and we have to give test labels and Y prediction. So this is basically Y, and this is Y prediction. So you have to give your original labels and the predicted label as the input to this function, and finally you are calculating the square root. For mean absolute error, you have to write matrix, because inside the matrix everything is here, matrix dot mean absolute error, and you have to give the inputs, that is, this is your Y and this is your Y prediction. Similarly for R square, again R square is present in our matrix, so matrix dot R2 score, again the input is same. So in all these three matrices, the input is same, that is, this is your Y, or here you are calling it test label, this is your original labels or target labels, and this is your predicted label. So if I run this cell, I will get the values of all metrics. So this is 61975247. Let's go back and compare. So this is 5247 and this is 6197. So we can see that all these values are same. So basically in this project one, which we have just completed, we have done two things. So we have applied least square methods with two different methods. That is, we apply least square method manually. When we apply least square method manually, we did not use scikit-learn library, which is a library for the machine learning task. We completed every step manually. Even we calculated our matrices like root mean square, mean absolute error, and other matrices manually. And we find all these values. We do every step manually. We did not take advantage of scikit-learn. After that, we compare our manual performance with the scikit-learn performance, and we can see that our performance is 100% accurate, and it is same as that of performing scikit-learn. Now, which thing is better? That is, we need to do regression manually using least square, or we have to use scikit-learn. So student, my advice is to always use scikit-learn, because this is a standard library. It is taking a very less time. It is taking a very less steps in order to solve your linear regression problem. The purpose of this project was to make you learn that how you can manually apply least square method as well. And also you can compare the performance of your manual calculation with the performance of scikit-learn. So I hope you understood this project one and you have learned a lot from this project. Thanks for listening, and I will see you in the next lecture.